Hello, and welcome to this example on how to use and compute conditional probabilities. Um, Today, we're going to talk about an example where we have two situations, infected and not infected of COVID-19. And then we have, on the other hand, positive or negative test result. Before I go over the example on how to use conditional probability, I am going to walk you guys through the basic formulas of conditional probability. So we're going to say, in general, the probability of A given B equals the probability of A and B intersection over the probability of B. Right? So we are going to be using this formula over and over again to actually solve or go over the exam. So let us start with this situation. We know the sensitivity of a COVID test is 95.2%. That is telling us the probability of positive given infection, a positive test given infection. Specificity is going to give us the conditional probability of negative given not infection. And then we are taking as given that the probability of infection is 3.6%, right? So what that is telling us is something that relates to the chances of different events. So right here, we're going to say the probability of infection is 3.6. So we're assigning some sort of like measurement of the chances that, in fact, we have infected people, and that relates to this situation right here, right? So this is what we call the probability of infection, and we're going to say this is 3.6%. And then the probability of positive given infected and negative given infected will be, or will relate to the formulas that I mentioned that we're going to use over and over for this specific example. So the probability of positive given infected is going to be equal to the probability of positive uninfected over the probability of infected. And then the probability of negative and given not infected is going to be equal to the probability of negative and not infected over the probability of not infected, which is very useful because now we can try to figure out what is known and what is unknown. We know that the conditional probability equals 95.2%, and we also know the probability of infection equals 3.6. So somehow we could actually reset this denominator as 3.6 instead of probability of infection, right? So we could write right here, we could write simply 3.6%, right? 3.6. And then for the next equation, we know that the probability of negative given not infected equals 98.9. And we also know that if the probability of being infected is 3.6, we know that the probability of not being infected is equal to the complement. That means that I can totally replace or change this denominator for the complement of 3.6. And the complement of 3.6 in this case would be 96.4%, right? So so that's the information that we have. We have 95.2 equals probability of intersection over 3.6. In other words, we can solve for the probability of the intersection, positive and infected, and we can solve for the probability of of the intersection negative and not infected, right? So I can totally do that, and that's what we do in the next slide. So in the next slide, I am going to kind of like figure out exactly that. The probability of negative given not infected, it's equal to 98.9, and then the probability of positive given infected is 95.92, and then I can totally solve for the probabilities of the intersection, right? So the probabilities of the intersection will be the multiplication of 95.2 times 3.6. That is going to give us 3.4%, and then the probability of this intersection negative and not infected is going to be 98.9 times 96.4. That 96.4 is the complement of 3.6%. We get 95.3%, and I am going to organize this in a table, right? So this table, it's what we call the joint probability distribution. It has on one side one of the two events, infected and not infected. On the other margin, you will find positive test versus negative test, and then the marginal probabilities on these margins are equal to the probabilities of infected. So the probability of infected will be this 3.6. The probability of not infected will be also on the margin, 96.4. And now in the intersection here, we will have the probabilities of the intersection. So infected and positive is going to be 3.4, not infected and negative 95.3, and I just computed those. Now, why do we care about that? Well, we care about that because we can now figure out all of the other probabilities. If this 3.6 it's the marginal probability, that means it's the total probability of infected. Well, it has to add to the probability of infected and positive plus infected and negative. In other words, I can figure out this as the difference between 3.6 and 3.4, and that will be 0.2%, correct? And then in a similar fashion, if I take 96.4 and I subtract 95.3, that is going to give me the probability that I have right here as not infected and positive, right? So that is exactly what I do in the next step. So now I have the 0.2% for infected and negative, and I have 1.1% for not infected and positive. And because I have the full table, the full joint distribution, I can now add 3.4 plus 1.1. That's going to give me 4.5% as the probability of getting a positive test. And then 0.2% plus 95.3 is going to give me 95.5, which will be the total probability of negative. And with this, now everything is relatively simple, because now I can compute any probability. Once I have this joint probability that is a 4x4 table, now the sky is the limit. Now I can compute anything that I want in terms of conditional probabilities. So let's say I want to figure out. Let's say I want to figure out, for instance, let's say I want to figure out the probability of infected given negative, or I want to figure out the probability of not infected given positive, right? So with the formulas of conditional probability, we know that this is probability of infected and negative over probability of negative. And then for this one, probability of not infected given positive would be probability of not infected and positive over probability of positive. But we have all of those pieces of information. We already have all of those pieces of information in the table that I just computed, the so-called marginal joint probability, right? So if I want to compute the probability of infected given a negative test, well, I can use my formulas. Will be simple, very simple. Will be the probability of intersection infected and negative, which is 0.02%. So that is the probability of intersection of infected and negative, divided by the probability of negative. And I know the probability of negative is right here, 95.5. So if I take that, it's telling me that the chances will be 0.18%. So the probability of getting being infected, given that I got a negative test, it's kind of small. It's 0.18%. Another thing that we can compute is the probability of not being infected given a positive test, right? So the probability of not being infected given a positive test will be the intersection between not infected and positive. And the intersection between not infected and positive is right here, 1.1% over the probability of positive. And the probability of positive is right here, is 4.5%. So if I take that fraction, I get 23.6%. So this is telling me that conditional on getting a positive test, the chances of not being infected are certainly close to 23.6%. So the message here is that these COVID tests are designed such that if you get a negative, you are kind of certain that you don't have the infection. However, if you get a positive test with about 1/4 of probability, you are not infected. I hope this was beneficial, and I look forward to seeing you soon.